Um, Last lecture, thank you for sticking with me. Hopefully you had fun. So, in the last lecture, we had little time to derive everything about the collisional-Boltzmann equation and the diffusion coefficients. But if you remember, at the end, I mentioned three particular things that really helps us solve these gravitational n-body problems. One is typically for large n systems, relaxation time is much longer than the crossing time. Okay? And we have also mentioned that individual deflections are small, okay? And we also mentioned that, so what these two conditions mean is that per orbit, total deflection will be small, so you can get some kind of orbit averaged treatment of the actual n-body system instead of calculating the full forces at every time step. And in addition to that, since the density distribution is such that most of the stars are somewhat near the center and far away near the halo, you don't have a lot of density. So you also know that most of the deflections from other stars will be at impact parameters that are smaller compared to the actual size of the whole system. So all of these allows us to do some kind of approximate solution of the actual n-body problem instead of calculating the pairwise forces at very short time steps. Okay? And one of the there are several different approximate methods. For example, in principle, you could take the Fokker-Planck equation and numerically solve it. But the problem with that is you are starting with a smooth distribution and you are solving for relaxation. So any physics that works on a different time scale than relaxation is very hard to resolve. So you can, people have tried to give prescriptions of, say, how stars evolve, just due to stellar evolution, which is at a much shorter time scale than relaxation. But usually these are not very accurate. There are two other types of Monte Carlo methods. This is also numerical solutions. One is called orbit following. So there the assumption is per crossing time, the effect of these deflections are local. So most of the stars will be close by. And you can assume that all of these deflections are independent of each other because after one deflection, it will take several orbits to have another deflection. But there also, the time step you need to do is some fraction of the crossing time. And the power of this method is typically you start with a discrete field. So you have n stars, all with masses and radii and velocities. And then you convert it to action angle variables, for example, energy or angular momentum that people always use. And then you say that I will follow a selection of stars' orbit in this potential. But each star is not a single star. It represents all stars that have similar pericenter and apocenter distances. And then you rigorously follow its orbit, and that's how you can solve a large n system, because you are actually not following the orbit of n stars. So the power of this is you still retain the information of the discreteness of the field, and you also retain some representative phase information for stars in its orbit as time goes. So these kind of Monte Carlo methods can be powerful when phase becomes important. So for example, if you have resonant relaxation near a supermassive black hole, or at early times when you haven't reached virial equilibrium, and the evolution is really governed by violent relaxation. In situations like this, people use this orbit following method, initially proposed by Spritzer. There are several groups who are actively developing codes for this orbit following type Monte Carlo, and they are typically used to resolve stellar motions around galactic centers. There is another type of Monte Carlo method that essentially, it comes from the realization that phase-space diffusion happens on relaxation timescales, which are much longer than the crossing time. So there is no point in actually caring about where a star is at any given time in its orbit, okay? So this is a fully orbit averaged method, and the main benefit of this is your required time step is now a fraction of the relaxation time rather than a fraction of the crossing time. So you can go through several relaxation times with taking very few integrations. And that becomes powerful for any spherical system because you assume that statistically speaking, everything that there is no anisotropy in the position. So these kind of Monte Carlo codes are called Henon-type Monte Carlo, okay? And that's what we use. And it has been very successful in describing nuclear star clusters. So any kind of strictly spherical systems, these are very useful. And also in systems where resonant relaxation, which depends on the phase in orbit of a star, when that is not important, you should always use Henon Monte Carlo, and if n is large enough. So a general structure of this code, if you look at this, you start with an n-body model. By n-body model, I mean you have n stars, you have each of their masses, and their position vector and velocity vector. And then, since this is spherical, you calculate the energy and angular momentum of each of these stars, and then you say that I don't care where exactly the star is, since my potential is spherical, I will treat this star as a spherical shell of the same total mass. This way you can calculate the potential of all stars. And then you say that I know that all of these small deflections that are happening over a relaxation timescale are independent. So they will be somewhat like a Gaussian. And the mean and dispersion of this Gaussian of delta V depends on the diffusion coefficients that you calculate in advance. And then you say that I will draw one delta V from this distribution, and that delta V will be some function of the mean delta V as a result of all the small angle scatterings during that time. And I will just change my orbit using that mean delta V. Okay? So this is often called a super encounter. So you are not really resolving all the small delta V's because you don't need to. You take a representative delta V that essentially represents the cumulative effect of all of these random delta V's. After you change the orbit, you update the energy and angular momentum. You calculate the new orbits. And after you calculate the new orbit, remember, after you have distributed the mass in spherical shells, you have gone away from the discrete representation of the model, right? So you need to get that back. So you calculate new orbits, and then you Monte Carlo the new positions and velocities for each star given its new orbit. Okay? So essentially, this is equivalent to saying that I don't care about phase of a star in an orbit, and each time I need their actual positions and velocities, I'll just randomly draw them from an orbit, which with some weight, essentially by the time a star should spend in that phase in that orbit. So it's roughly 1 over V. Okay. It is, yes. So, but I'll come to why this is more powerful than simply evolving a probability distribution. So now you Monte Carlo the new positions and velocities. So essentially, at this stage, so you started with an n-body model. At this stage, you have a new n-body model, which is a valid solution of the Fokker-Planck equation. But instead of having a smooth density function and smooth probability distribution, you again have a discrete stellar representation. So in principle, if you think deeply, this n-body model, if you calculate all the forces at all delta t, may or may not come to this point. These are chaotic systems, right? But this n-body model will evolve to something that has the same statistical properties of this n-body model. Because essentially, you have solved how the probability distribution is evolving over time. And after this calculation, you are getting back an n-body model. Yes? Typically, we assume one of the king profile families. So as soon as you say it's a king model of some concentration or W naught value, and the total mass, and the total n, that uniquely defines a representation of a valid spherical distribution function of n stars. You're getting the total mass in each shell, and then you are calculating the potential, and then you are calculating the energy and angular momentum. Essentially, that means you know the pericenter and apocenter of each orbit. And then you give deflections for each of these orbits, and then calculate energy and angular momentum in the new orbit again. No, orbit of all individual stars. So each individual star, let's say you have a star of mass m1 at some r1 distance. You say that instead of having a star at that location, I assume that the whole m1 is actually a spherical shell at r. That allows you to easily calculate the potential as a function of r due to these stars. As a result, it becomes very easy to calculate the energy and angular momentum of each of these spherical shells. And then you do the deflection and the new energy and angular momentum calculation, and then you find an orbit. And the reason why spherical shell is okay is from the basic assumption of spherical symmetry. So if you have some value of energy and angular momentum, it could be oriented in this direction, that direction, anywhere, right? So you don't care about that, how exactly it's oriented. That's what it really means in distributing everything in spherical shells. Because this is a valid solution of the Fokker-Planck equation. Because these deflections you give are dependent on the diffusion coefficients. So that's how a Fokker-Planck evolution will happen. So that's how the distribution function evolves in time. Right. So essentially, in all you are doing in here is a numerical solution of the Fokker-Planck equation. But you started with an n-body model, and at the end you got back an n-body model. Okay? So the power of that is now you don't care about the distribution function per se, because you have individual stars, and they all have their individual properties. So whatever additional physics you want to add, for example, stellar evolution, binary star evolution, there can be strong scattering, there can be tidal truncation due to the tidal forces in the galaxy. All of these you can add on because you actually have individual stars, and you can tell what that individual star is doing in that time. Okay? So that's why, so there are two major groups who use this kind of codes. One is at Northwestern University, which has a branch at TIFR now, and one is in Poland, I think guided by Mirek Giersz. Yes. Cumulative effect of the encounters. So you can show that because delta V's are small, and because T cross is much less than T relax, you can show that all of these delta V's are independent of each other. So in the phase space, the star is doing a random walk. And so essentially from central limit theorem, you can show that the delta V's during all that large delta T are distributed as a Gaussian. And then you know that the cumulative effect of all of these delta V's will be equivalent to having a mean delta V of that Gaussian and a dispersion of that Gaussian. So this is the first moment of delta V, and the dispersion will be the second moment of delta V. And if you remember, Fokker-Planck approximation is saying that since delta V's are small, I can expand it in a Taylor series, and I will truncate it to the second order. That's exactly what this is. So the question is, real question is, since this is a gravitational school, so we need to come back to black holes because they're fascinating. The real question is, do globular clusters now have black holes? And this question has a decades-old history, and the answer to this has dramatically changed in the last 5 or 6 years. And this is the reason. So I have shown you these time scales before. So the relaxation time is related to the crossing time like this. And typically for globular clusters, these are the values. Okay? And I also showed that the mass segregation time scale of some ith species is dependent on the average mass in its neighborhood divided by the mass of the ith species times the relaxation time. So let's look at some numbers for black holes. Okay? So let's say that this is about 0.5 solar mass. That's roughly the average stellar mass if you assume a standard IMF. And let's say this is about 10 solar mass. Typically the black hole, average black hole mass is about 14. So mass segregation timescale for typical black holes would be about 50 million years. So it happens almost instantly relative to the age of the system. And then you know that if you now think about what is the velocity dispersion only in the black holes and how long it will take for the black holes to evaporate from the system, then these are the relevant quantities, order of magnitude. So this is the velocity dispersion in black holes that is roughly equal to, this is the escape speed for the black holes that is roughly equal to 4 times the velocity dispersion. So that was one of the tutorial problems yesterday. And then typically these black holes sink. So let's just say that they stay in some 1/10 of the cluster's size within. Then you can calculate what are the crossing times for black holes. That's roughly this. The number of black holes you know is roughly 10 to the minus 3 times n. So the relaxation time for black holes is roughly 10 to the minus 4 times the relaxation time of the cluster. And the evaporation time of black holes is roughly 100 relaxation time of black holes. So that's roughly 10 to the minus 2 times the relaxation time of the cluster. That's roughly 10 million years. And this was first pointed out by Spitzer in 1969. His analysis was a lot more complicated and more rigorous. This is this famous Spitzer instability, but for black hole subclusters. But this is, if you don't care about the details, this is roughly what the argument is. So black holes sink to the center rapidly, and they evaporate rapidly. So all the story that I told you very briefly about how black holes sink, then they interact with each other, and through strong encounters, create new black hole binaries that can later merge and be detected. All that story becomes kind of irrelevant because if you don't have enough time to work with the black holes, then nothing really works. Okay? But Spitzer was wrong, and we understood that only recently. So the first thing that came about that forced us to think about this problem again, so actually not only Spitzer, so after Spitzer there were tens and 20s of paper that essentially developed the same idea, and they all showed in many different ways why old, dense stellar systems cannot have large number of black holes in them today. That all changed from about 2007. Well, not really from then, because everyone kind of ignored this. Because it is so easy computationally to not worry about the black holes. Because black holes sink to a very tiny volume, and then you have to resolve that volume, and computational cost increases very quickly. So what I'm showing here is a very interesting result, and this was a superluminous X-ray binary that was associated with a globular cluster in this galaxy. And they showed that the X-ray luminosity is varying very rapidly. So why both of these are important? So you can have very high X-ray luminosity that you cannot explain by one neutron star. But if you are not really resolving each individual neutron star, in principle, you could have 10 neutron stars in there. They are all emitting in X-ray. And overall, you will have a very high X-ray flux. But if that is the case, then you will not have rapid variability because what you are getting is some average quantity. Okay? So this rapid variability hinted that this probably is a single system that is accreting very highly. Okay? And no, you cannot explain this with neutron star mass. So this was the first black hole candidate that was reported in a globular cluster. And then after VLA was upgraded, then a new method of black hole candidate discovery came up. And that is comparing the X-ray luminosity with the radial luminosity of systems. So VLA allowed them to identify individual sources in Milky Way globular clusters. And so far there are, I think, 4 candidates, 2 in M22, no, 2 in M62, 1 in M22, and 1 in 47 TAC. So the argument is as follows. If you plot all the accreting systems in the X-ray versus radio plane, radioluminosity plane, then the neutron stars kind of populate this region. White dwarfs are below this region. And this is the region where the black holes live. These are the black hole X-ray binaries in the field, all the black ones. And they all follow this kind of relation. And the colored dots are the black hole candidates that were identified in M22, M62, and 47 TAC. Right. So another interesting thing to note is in terms of cluster properties, M22, M62, and 47 TAC are very different from each other. So it doesn't seem like any particular type of globular clusters have these black hole candidates. It seems like it's ubiquitous. And then they argued, you will see it was a wrong argument, but they argued that only a small fraction of black holes actually have a companion. And among them, a small fraction of companion are currently actively accreting. So if you see one, that probably means there are hundreds. The inference was correct, the argument was wrong, and I will show you why. And then, even more recently, this year, they found a radial velocity candidate for black holes. They found a close to turn-off main sequence star that has very high radial velocity. And by fitting this radial velocity, they found mass that cannot be a neutron star mass. So that's the minimum mass of the unseen companion. So clearly, some black holes live in globular clusters. This is now observationally verified. So let's look at why Spitzer was wrong. Spitzer was a smart guy. He usually didn't make mistakes. What I'm showing you here is an evolution of Lagrange radii. So Lagrange radii are defined in the following way. So if you look at the 0.1% Lagrange radius, that means 0.1% by mass of some species is contained within that radius. Okay? And in this figure, I am the solid lines denote Lagrange radii involving black holes only, and the dotted lines show anything that is not a black hole. Okay? And the colors are the same, so 0.1% is the black, and so on. So what you can see is that about 10% by mass in black holes do separate from the rest of the cluster. So that's where the rest of the cluster is at this time, let's say. And roughly about 10% by mass black holes are separated in space. That is a very different picture from what Spitzer assumed. Spitzer assumed that all black holes separate from the cluster, all black holes evaporate over several relaxation times. This is a simulation. And 10% by mass is actually much lower percent by number, because typically the heavier black holes sink first. So the average mass in the black holes that have already sunk is higher than the average mass that are still out there. So this dynamical decoupling doesn't really take place in real systems. So let's no, this is whatever is remaining. Yes. Because that's what really matters. So, yeah. Okay. So what are these spikes? Zoom. Make it bigger. So this is one of these spikes. So it goes from here to there to there. Okay? And now what I'm going to show you is for each of these different points, I'm showing you the shape of the cluster potential. And in the red dashes, I'm showing you the innermost 50 black holes. And the blue dashes are showing you the innermost 50 non-black holes, their positions. Okay? So when the Lagrange radius was there, this was out of a collapse state, the potential looked like this. The black holes and the non-black holes were mixed. And this is not even all black holes. This is the most segregated, most decoupled black holes we're talking about here. So it goes towards more and more towards the collapse, and you see that only a few black holes are leaving the others and going more and more into the potential. The potential is becoming deeper and deeper. And then, somewhere here, something like this happens. So the density is so high that you can even form a three-body binary, even if all the black holes were initially single. So that was one of the other problems yesterday. So you probably have seen that the probability of forming a binary from 3 single stars is very low, but it is proportional to the density. Okay? No, we have stars. They evolve. So we know everything about that star. In the snapshots, we have the stars and the black holes, where they are, etc. So we can calculate the potential and draw it. Yeah, that's the beauty of these simulations. Ask me anything, I will tell you anything. Modulo the accuracy of the physics. Okay. And then after this, you can have ejections of black holes, because these are extremely high energy encounters, and escape speed from clusters are not very high. So in principle, you can always eject black holes. So ejection of a black hole from the deepest part of the potential means you are taking mass from where it hurts the most, right? So then whole cluster jumps up, comes out of a collapsed state, and you see the remaining black holes are now again totally mixed with the remaining non-black holes. So this whole argument of a dynamical decoupling was wrong. So everything in the timescale estimates where I multiplied by small numbers to make a very small timescale at the end, all of that analysis is wrong. Because only a few black holes decouple, and they don't stay decoupled for long. And you can see that the timescale is tiny from here to here. So what does it do? So we are now looking from a different angle. So before we were thinking what the cluster dynamics does to the black holes. And now we are thinking about what this black hole dynamics does to the cluster. So if you look at something like a core radius, so this is roughly equivalent to a King scale length in previous classes. And RH is the radius within which half of the total mass is contained. It's called a half mass radius. It looks somewhat like this. You see all of these spikes. You now know what these spikes mean. And the half mass radius keeps increasing. So as long as you have enough black holes, this black hole dynamics creates so much energy at the center of the cluster that the whole cluster keeps expanding slowly. And that's how the evolution looks like. But the question is, can we look at a globular cluster today and measure something that we can measure and tell directly whether that cluster contains a large number of black holes today or not? Because no matter what we say, if we cannot get observational proof that globular clusters do indeed have black holes today, we cannot really believe what we are saying. So one of the things that any observer measures, this is the most standard thing that they measure, is a surface brightness profile. So this is the 2D projected distance from the center, and this is a projected luminosity density of the cluster. And what I'm showing you is the surface brightness profile from this model at two different times. The red is at a non-collapse state, and black is at a collapse state. So essentially, there is zero difference between the two surface brightness profiles. And you can easily understand why. All of that interesting dynamics is being done by a handful of black holes that you don't even see. So what you can see, all the luminous things, there is zero effect that you can easily observe and infer whether the black holes are doing this in a cluster today. That makes it very hard to infer directly whether a cluster today has a large number of black holes. But Monte Carlo simulations. Yeah. We start with very good initial conditions, we evolve it for 12 billion years, and we see all of this. No, this is model. So in no observation, you will see this. The point is, although the cluster is doing that, if you actually observe the cluster as if it is out there in the Milky Way, and only take into account the observable properties of that model, then you see no difference between a completely collapsed state and a non-collapsed state. Fluctuations of what? We can talk about that later. I will tell you why it doesn't work. Okay, so we started with something really interesting. So the whole business of black holes may be remaining in globular clusters started with X-ray observation, right? So and the argument was, if you find one, there may be hundreds. Let's see if that works. So in principle, an X-ray binary, X-ray black hole binary, is at least a black hole that has an extended star that is mass transferring now, right? It may or may not be bright enough to be detected, but that is at least what you need. So what I'm showing you, ignore case 1, case 2, case 3, they are different types of physical input, but take any panel of your choice, and what you should look at is this is the number of mass transferring black hole binaries as a function of the number of total black holes remaining in the cluster. And in these models, the number of total black holes in the cluster varies from 1 to 1,000, but the number of mass transferring black hole binaries remain insensitive to the number of total black holes. And this is understood well, actually. So you can imagine a cluster like these shells. So this is dominated by a few black holes. This is where the black holes can mix with the other stars. And this is all other stars. So since all binaries typically get created dynamically, this is the place where you can create black hole, non-black hole binaries. And due to black hole dynamics, if you have a large number of black holes, then it gives so much energy to the rest of the cluster that this gets puffed up and the density in the mixing zone goes down. So the rate of creation of black hole, non-black hole binaries goes down, because rate is, remember, density times cross-section times velocity dispersion. And when you have very few black holes left, the density goes up, but the total number of black hole, non-black hole binaries you can create is limited by the number of black holes you have. Okay? So it's a competing effect that makes the total number of, so this is a rate of net creation of black hole, non-black hole binaries as a function of total black hole, and it is essentially constant over large ranges in black hole numbers. Is there anything else we can do to infer something? The answer is yes. These are some of the requirements. These are robustness requirements. It's not very important at the moment. But if you think about it, this is one of the most fundamental things you see in any cluster. Okay? That's the color magnitude diagram. And the whole physics of black holes being or not being in the cluster is governed by mass segregation process. Heavier things sinking and lighter things going out. Globular clusters are relaxed, yes. So, if you, but the problem is black holes you don't see. So let's concentrate only on stars that you see. So these are the stars that you see. But even here, you have a large range in masses in stars. So how about you take the really massive stars from here and compare their radial positions relative to the low mass stars that reside here. So this is showing a cumulative distribution of radial positions in projected radial positions of the two species. Red is the high mass species, blue is the low mass species. And you can see that they are separated. Okay? So cluster is like onion shells of decreasing mass with increasing radius. And it has some number of black holes. For this case, it's 41. And let's see what happens if you increase the number in some different model. You do the same figure. As you can see that as you increase the number of black holes, the separation between these two species decreases. This is because when you have a large number of black holes, they sink and they keep giving energy to the rest of the clusters, right? But since energy flow is a diffusive process, it affects whatever star is close by more than whatever star is really far apart. So whatever is the effect of the black hole's mass segregation affects the highest mass visible stars more than the lowest mass visible stars. So this puffing up happens more on the giants and less on the low mass main sequence stars. As a result, if you increase the number of black holes, the mass segregation measure between the visible species of the stars decrease. And you can do hundreds of these models, and this is how it looks like. It's kind of noisy. This is the number of black holes per number of per cluster star, and this is a measure of the mass segregation. So this is actually the distance between the two medians of the cumulative distribution. So what you can do, and we have done that, is run hundreds of these models, take this data, create a 2D density distribution that will work as a calibration tool. And then you measure the same thing for observed clusters. So we did that for 47 TUC, M10, and M22. And you can get a probability distribution of retained black hole numbers in these clusters. You can do this for any observed cluster where the data exists. Okay? And what you can see is the probability distribution have large spreads, and the spreads are essentially dictated by completeness corrections. So it's hard to see the faint low mass stars near the bright high mass stars. So you have to take into account all these uncertainties. But no matter what, you see that it makes sense from observable properties of these clusters that it has a significant number of black holes today. And it's actually impossible to exclude zero, because if you reduce the black hole number to very small values, then the black holes are not dynamically important anymore. So few or zero will make no difference. So now we know that, now we have indications that black holes stay for long times in a globular cluster. And we have some empirical evidence in observed globular clusters that indeed, at least in these clusters, it seems to have a largish number of black holes to present day. So just to remind you what the basic process of creation of black hole binaries in a star cluster. Most massive black holes sink to the center. High density allows new binary black hole formation, independent of whether the black hole initially was in a binary or not. And this can be in two different channels. You can create 3-body binaries using 3 black holes, single black holes. Or you can use exchange interactions where the initial binary was not black holes, and then you exchange black holes into it one at a time. And then through repeated encounters, so once you have a binary black hole, because of their very high mass, usually it will be very hard. And flyby stars would have to have very high velocity to actually break that binary. So if it doesn't break the binary, it typically shrinks the binary, and these encounters are super elastic. So black hole binaries, once created, keep shrinking, and at some point, the orbital speed becomes high enough. Okay, so in these superelastic encounters, the recoil speed is of order the orbital speed of the binary. So at some point, it shrinks enough that the orbital speed is larger than the escape speed. And then, at that point, the recoil will take it out of the cluster, and then it will not be affected until it merges. Okay? If the merger timescale is shorter compared to the interaction timescale, then it merges within the cluster. And this is important for extremely high eccentricity binaries. So in principle, you can have eccentric captures that give bursts of gravitational wave radiation and then merges very rapidly. In those cases, they don't have to be ejected. Okay? But ejected or not, the property of the black hole binaries that will merge depends only on the cluster's dynamical properties. So everything is going radially down to the center is true only when you have zero angular momentum. That's not true here. So everything has some finite angular momentum. I think the localization is not good enough. So another interesting thing, so let's take a deeper look at the kinds of binary black holes you form in dynamical environments and how they are different from isolated formation. Okay? So remember in the first class we talked about isolated formation. So one thing is very clear, that the formation is extremely a random process. Okay? So let's look at something really cool. So I am going to show you results from two different models that are identical initially to each other, except in the red model, I have all high mass stars initially in a binary. And in the black model, I have all high mass stars initially single. So in the isolated case, this model, the black model, will produce 0 binary black holes. And this will create some. Okay? So this is showing the number of black hole binaries created in a cluster and remaining in the cluster as a function of time. And roughly about a few relaxation time scale later, the two models converge to a fixed value. This is because it doesn't matter where the high mass star was born. It doesn't matter whether that black hole had a companion or not. They all come to the center. They all go through the chaotic dynamical processes. And the black holes binaries they create are dictated only by the cluster's properties. The same is true if you look at the black hole binaries that are ejected. So there are too many lines, but this panel is the red model, this panel is the black model, and you should look only at the green line. That's the number of black hole binaries ejected. Again, you see, roughly about here, the number of black hole binaries created and ejected converge in both models. So this is not only number of black hole binaries in cluster. This is black hole binaries formed in general. So let's try to understand this, these time scales and relevant properties of the cluster. And that actually will help understand why not only the number, but also the properties of these binary black holes are dictated by the cluster's dynamical properties. So from virial theorem, we know that the velocity dispersion is roughly is dependent on the cluster's properties. We also know that escape speed is also dependent on the cluster's properties. So we know that only the binaries that have a binding energy that is greater than the kinetic energy of the incoming particle survive. So this condition must hold for binaries to be there and interact and take part in exchanges. And by the time the recoil speed, which is of order the orbital speed, becomes greater than the escape speed, which is related to the cluster properties again, that binary is removed from the cluster, right? So in principle, which binaries interact, what their properties become after several of these interactions, and with what properties they are ejected from the cluster, are all related to the density distribution and total mass of the cluster. Okay? So let's look at some toy illustrations. So you have one black hole binary sitting at the center. It had an encounter, it shrunk a little, It got a recoil speed that's of order the orbital velocity. Then mass segregation brought it to the center. But now its orbital velocity is faster because it's shrunk. So now, after the encounter, it will go a little farther. And it will keep doing that. And at some point, it will get out. And with what property it will get out depends on the escape speed. So, if you have a larger, more massive cluster, you will have a tighter binary that gets ejected. Okay? So the escape speed of the cluster determines the semi-major axis of the ejected binaries. It also determines the interaction timescales of the binaries, because the velocity dispersion also is a property of the cluster. So even in cluster mergers, where the merger timescale is shorter than the interaction timescale, how many of these will happen in cluster also depends on the cluster properties. So let's look at the typical in-spiral times for some masses and number of stars in a cluster, okay? Ignore this one. If you look at these panels, what I'm showing you is the in-spiral time scale for a binary black hole created in one of our models. And this was a model with n equals 200,000 initially. So as you can see that, sorry, it's hard to see this line. So this is roughly where the age of the cluster is, 10 gigayear-ish. So anything that is merging around within this is happening within a Hubble time. So for lowish n, you see a small fraction of the binary black holes merging, and they are almost all merging in the local universe. As you increase n, you have a higher fraction merging, and you keep doing that, and you get, by the time you get to 2 billion, almost all binary black holes created in that cluster will merge within a Hubble time. And if you look at the globular cluster mass function, then these numbers are also exactly where the peak of the mass function is. So not only these globular clusters are very efficient in creating binary black holes that will merge within a Hubble time and be relevant for LIGO, the globular clusters that are efficient are also the most abundant in the universe. So it's almost like whoever, if you believe in intelligent design, whoever designed the globular clusters, designed them for the creation of binary black holes, that would be detected by LIGO. Okay. So just imagine, throughout the universe, God created globular clusters so that LIGO can detect things. So this is some other properties. So you can look at how the total mass of these mergers vary over time. So what we are assuming is today, at 12 billion years, is redshift 0. And so that's roughly when the globular cluster formed. And the trend that you should see is that the typical total mass for the merging binary black holes is going down as a function of time. And that is because you always process the most massive black holes first. So you create the binary black holes with them, and they merge, and then you bring in the lower mass ones, and so on. So that's why you get this kind of behavior. And there are 3 different types of dots. The blue is ejected mergers, so mergers happening after they got ejected. Let's call it orange. Orange is in-cluster mergers, and the black are repeated mergers. So in principle, you can have a merger, and if the conditions are correct, then you don't get a gravitational wave recoil kick high enough to eject that system. So then that merger product can merge again. Okay? So these repeated mergers can never happen in isolated systems. So that becomes an invaluable tool to distinguish between whether any particular merger came from dynamical channels or isolated channels. Okay? So yes, no, the repeated mergers depend on what we assume for the spin distribution. And ejected and in-cluster mergers are roughly 50. So actually, in the details of it, we don't put any spins to begin with. So after we get the mergers, we say that spin orientation must be isotropic because it's chaotic. So we assume some kind of birth spin, and we say, okay, if this merger happened with this kind of birth spin with random orientations, then what would be the kick? And then, right. You mean the mass distribution of different types? Quite far, because a lot of these ejected systems can actually be ejected very early. And in several billion years, it will probably be very hard to associate a black hole binary with its host globular cluster. It will still be in the galaxy. Typically, these ejection speeds are not enough to eject them from the galaxy. But that's a very good question. It'll be interesting to see what Gaia can do. It will not be relevant for the black holes because Gaia cannot see them. But from what Gaia can see, we might be able to have some handle on typically how long can you associate something ejected from a cluster to a cluster. There are very few cases where you can see a prominent tidal tail, but these are extremely weird clusters. Their evolution is being driven by the tidal truncation. So the tidal tail didn't have time to get diffuse enough that you don't see them anymore. For most global clusters, this is not true. So, what would you look for? 3D velocity. And if there must be some kind of clustering that follows the orbit of the cluster. I don't know, I'm just making things up based on your question. 100-ish kiloparsec. Oh, no, so globular clusters you can see in other galaxies. In very distant galaxies, all you see is the total light. And these are the only things that you can resolve. So that makes actually global clusters interesting for many different branches of astrophysics. Just by looking at where the globular clusters are and from total light what the mass is, you can constrain the potential of the host galaxy. And people actually do that. Any other questions? Oh, yes. Thank you. I was supposed to talk about that. So the red line is roughly where you'd think So the red line is roughly where you think the above which only repeated mergers dominate. So there is a new kind of a new idea that there must be a maximum mass of black holes. So if you keep increasing the mass of the zero-edge main sequence star, you cannot create black holes from them above a certain mass. And this comes from pair production instability. And it's yet to be determined whether that really happens or not. But in this model, we have enforced that criteria. We say that from single stellar evolution, you cannot create black holes more massive than this. So anything above this red line is a repeated merger. So if you see repeated mergers, it definitely is coming from dynamical channels. And this is roughly the distribution in number and in mass. And this is what Ajith was asking me about. So whether or not something will merge repeatedly depends on the gravitational wave recoil. So this is not the same recoil as the dynamical encounter. This is after merger, gravitational wave can give a recoil. And that recoil speed depends on the masses, spins, and their orientations. So depending on what you assume to be the Barth spin distribution, this is unconstrained completely, no one knows. You can get different levels of importance for repeated mergers. But in general, if you see a pre-merger mass in LIGO, that is greater than the maximum mass in black holes, then it definitely came from a dynamical channel. Another thing is eccentricities. So because all the binary black holes are created dynamically, you expect them to have a thermal eccentricity distribution. But typically, it turns out, so what I'm showing you here is the eccentricity as a function of the gravitational, the dominant gravitational wave frequency. And the gray lines are coming from globular clusters. Blue lines are coming from galactic field after one common envelope. Green lines are after zero common envelope. It doesn't matter. So essentially, you can compare the gray with the colored. So although a large number of these binary black holes can start with very high eccentricity, by the time they come to the LIGO band, they decay. This is for the majority of the normal binary black holes that are created through dynamical encounters. But there is one channel that can be very interesting that contributes to very high eccentricity, so in excess of 0.1. So these are gravitational wave captures. So in principle, you can have two black holes that have a net positive energy. Initially, they were unbound, but just unbound. And they come so close to each other, the impact parameter is so small that the burst of gravitational wave radiation makes the two things bound. And typically, this impact parameter is so small that it merges rather rapidly after the capture. The same thing can also happen in bound systems. So you can, in principle, have such a high eccentricity in a binary that the same method may work. And because they kind of form abruptly and starts radiating at very high frequency, that's where you see them. So by the time it comes to LIGO band, it doesn't decay the eccentricity because it almost is created in the LIGO band. I have to check. You can calculate that using Peter's equation. Maybe I will add that to today's tutorial problem. What? Right. So these are systems that are normal binaries. By the time it reaches, so initially it was a distribution that really peaked at high eccentricities. So thermal eccentricity distribution. And then majority of them decayed their eccentricity and came here. But a few were created there, so they did not get time to decay their eccentricity. So this is eccentricity at 10 Hertz. So this is the first time LIGO sees this binary. Right. So if the frequency is 10 Hertz, then there you go. Yeah. It doesn't have to merge rapidly, but if you are already at 10 Hertz, they do merge rapidly. So some eccentric mergers also will indicate dynamical production channel. And then I talked about spins. And this is an important tool because typically, if you remember, in the isolated channel, the binary black holes that will merge come through several stages of dissipative processes. There was tide, there was Roche-Loeb overflow, there was common envelope. So all of these dissipative processes typically make the eccentricities small. And since the binaries were formed together, so primordial binaries, you would expect that their birth spins are aligned if they are spinning. So in isolated case, you expect that the angle between the two spin vectors is not very misaligned. Okay? Some misalignment you can get from if you can play with exactly how the supernova cake works. Okay? But you expect that misalignment will not be very high. And the mass-weighted projection of the angular momentum on the spin is what LIGO measures. And remember that we don't know what is the birth spin distribution for black holes. So you can imagine for a curve that shows as a function of the total mass, so there's, you see what the chi effective distribution is for different birth chi. So if chi is 0, then you see something like this. So the different colors are different percentiles, and the white line is the median. So you see that after you detect a large number of binary black holes, and if nature is kind enough and we can detect a large number of these chi effectives, then we can make a distribution of them. And then if we plot that as a function of the total mass, then we see very different shapes depending on what the inherent birth distribution of chi is. And no matter what the birth distribution is, in isolation, for example, there will be no mass dependence. So everything is born misaligned, and they will stay misaligned. But in dynamical systems, you do see some kind of mass dependence, and that comes from roughly about where repeated mergers become important. So maybe there will be some signature in the mass versus chi effective. "40-ish, 50-ish is what people say. That's in the total mass. That came down. Well, at least I know that I am in a bet that says that if a pre-merger mass is above 50 solar mass within 100 LIGO detections, then I get a nice bottle of wine. So all of that is well and good. Dynamics do play an important role in creating very unique kind of binary black holes, and probably in the next 5 or so years, we will be either able to say that, hey, this came from dynamical channels, or we'll be able to make some inference of what is the relative importance of the two different channels, etc. Or who knows, there may be all kinds of different channels proposed by creative people. But I want to point out about some uncertainties. And that's where I will wrap up. So remember, in the isolation case, main uncertainty comes from the common envelope evolution. This is on top of all the uncertainties that are associated with black hole formation physics. So for example, we don't know, but as a function of metallicity, what is the birth mass function of black holes? We don't know what is the distribution of kicks as they form. These are unknown. We also don't have a very deterministic way to take a mass function at zero-edge main sequence for normal stars that we observe everywhere, and it's well constrained. How to take that and infer a distribution of black holes, black hole masses? We don't know. And the isolation formation channel, on top of that, will have the uncertainties related to the common envelope. So in the dynamical channel, there is no uncertainty on top of the things that we don't know about black hole formation physics, because everything is very simple physical process. It's just Newtonian gravity for most of the time, and they are all random, so you erase initial properties. So rates and properties don't even depend on what you assume for the initial properties of binaries. So the real question that helps both are, what is the retention fraction of black holes in globular clusters? That essentially dictates how long these globular clusters have to play with the binary black holes. And then we somehow need to find out a black hole birth mass function. And we somehow need to find out a black hole birth kick distribution. Okay? And I think that in 5 years, we will have a very good handle on these two using Gaia. But I will not get into that. So I have talked about we can have some indirect evidence. There may be other ways. And this needs large number of detections, and Gaia in 5 years probably will have a large number of detections. This is just a picture showing you the basic process. You have black holes coming in, they interact with each other, you create binary black holes. What you are seeing is a binary-binary interaction between two black holes and a black hole main sequence star. And you are seeing the lensing patterns. In absence of the black hole lensing, all you would have seen is a bright main sequence star at the center of the picture. Thank you. Questions? Typically, gas pressure is not important. Yes, I didn't talk about the different stages of globular clusters evolution. So let's say this is time, and let's say this is the core radius. So you start with some small core radius that is dictated by young massive star cluster observations. And then let's say this is 10 million years. During this time, stars are losing a lot of mass through stellar winds and supernova. Typical speeds of stellar winds and supernova ejecta is way higher than the escape speed from the cluster. So all that gas and material just leaves the cluster. So the cluster rapidly expands. And then at some point, the energy generation because of mass loss from the center becomes roughly equivalent to energy diffusion from the center through two-body relaxation processes. That's when it starts to stabilize. And then, roughly about a relaxation timescale, or some fraction of the relaxation timescale, the black holes sink and start dominating the energy production in the center. And then you see all these spiky things, and it keeps expanding. And then let's say that after you finish all the black holes, it starts a slow contraction phase through two-body relaxation. And it keeps increasing density near the center. And at some point, it stabilizes to some value. And this is where the visible stellar binaries become more important. So you have so much density that the binaries are interacting with other stars through superelastic encounters. And that's how the core generates enough energy and diffuses it to the halo that you somehow reach a quasi-steady state of the core. Once you finish all binaries, so you cannot extract energy arbitrarily from binaries, right? They will merge at some point. Once you finish all binaries, you will again see oscillation like this, because this oscillation essentially is you are increasing density so much that three-body binaries form. And once you form one binary, that's enough to make the core bounce. You can actually easily calculate a binary black hole that, say, will merge within a Hubble time, contains of order the same energy of the whole binding energy of the cluster. Okay. So the time scales are important. for most cases, we are seeing that this is already 12 billion years. Okay. But it kind of depends on what the initial conditions are. Yes. Gravitational wave recoil is totally dependent on the binary black hole. Well, whether or not it will be ejected depends on the cluster's properties. We can take a look, but it doesn't really matter because that's not what you see. So if you see a merger, all you see is two black holes. You don't know where they came from. You know what their masses are. Yes. I could not hear you at all. Yes. Right. So the gravitational wave recoil speed is dependent only on the binary. Whether or not, because of that recoil speed, the merger product will leave the cluster is dependent on the cluster. And then once that merger product stays in the cluster, and if it merges again to another thing, that surely is a high spinning merger, because this thing that merged is definitely rapidly spinning because all of the angular momentum came to the spin. So independent of what you assume for your birth black hole spin distribution, if you catch a repeated merger, chances are it will have a very high chi effective. Yes. So the total mergers actually go down in general. And repeated mergers are more important at high redshift. That means early in the cluster's life, because as a function of time, the cluster becomes less and less massive. So it's easier to keep the merger products when the cluster was more massive. That's why you see a trend like that. We had an old rate that is now extinct. So I don't want to give you the number because we are working on it now. Let's say it's a few tens, for sure. Okay. Thank you. I hope you enjoyed.
Yes, we are coming to the sort of end of the lectures of the summer schools, and I would like to thank Sourav on behalf of ICTS and the organizers for giving this excellent set of lectures on a very cutting-edge topic, such. And we wanted to use this opportunity to thank several teams, several people who are behind the scenes. One is, it takes a lot of effort from a lot of people to organize a program like this. So I would like to first thank the program team who had been doing an excellent job of coordinating the entire effort and really had been the backbone of the whole ICTS programs. In particular, this is Divya, Gayatri, and the AV technical team who had been doing the recording because this is these lectures are meant to be a resource for many people who are not here. So we hope that this be a very useful resource. So Naveen, Arun, Gopi, and Chantaraj have been doing a lot of work. And of course, money is a very important matter, and we would like to thank the accounts team represented by Sini here, who would be refunding all of your travel expenses very soon. and Baswaraj and the transport team front desk for arranging all the local transport and so on. And of course, there is a huge, large team managing the facilities, guest house, housekeeping staff, etc. And a lot of work goes behind this thing. And the web team who have been putting all these resources available for the full community. I would like to thank all the lecturers, Andrea, Kenta, Tejasvi, and Sourav, for giving a fantastic set of 4 courses and a really nice set of lectures. I would like to thank the tutors who have been organizing the tutorials, which means really an integral part of this program, which includes Ajith, Gayatri, Haris, Krishnendu, Salim, Rahul, Shilpa, and Sumit. Finally, I would like to thank the ICTS group members who have also done a huge amount of work in selecting the participants, and you should thank them for being here because they are the ones who selected you. And in particular, Sumit had been essentially functioning as basically an organizer who is doing a lot of back-end work. And finally, I would like to thank on behalf of the organizers, Bala, Arun, and ICTS, all the participants, because this is part of an effort to build a community of gravitational physics and astrophysics in India, and we hope that you will take a lot of knowledge and lessons and ideas from here, and you would make a very good use of this. Thank you very much. Also, in the next sort of 5-10 minutes, so we want to get some quick feedback. We take your feedback very seriously. We have been collecting feedback